Swayam Prabha. Digital India. Educated India.
Welcome to lecture 4 of week 4 in this Muffler Acoustics course in the NPTEL series of lectures. Well, we couldn't quite complete the sudden area discontinuity in the last lecture 3 of this week, but we will probably take it up today in this lecture, and let us get back to our diagramming towards the end. So, sudden expansion or sudden contraction, that is what constitutes a sudden area discontinuity. So, you see the schematics here. So, suppose you have a pipe like this, and if you from the side view, and if you look at from the other side, it is probably like this. So, the idea is that so this is like the diameter of the smaller pipe, and this is the diameter of the bigger pipe. So, basically whenever the wave comes, it gets a lot of area to expand into, and suddenly, so there is a sudden increase in the diameter. So, if this diameter is say D, this is capital D. So, D is typically much greater than D. You can have the other scenario, of course, where you have sudden contraction, in which case this would probably be the same, something like this. So, again your basically the idea is D is much greater than small d. What happens here, the wave either gets sudden area, a lot of area to expand into, or it suddenly is forced to contract or propagate through a much smaller area. So, both of them, under both situations, what we have is basically a significant part of the acoustic wave that is carried in the forward direction is forced to be reflected back into the system. So, if you have a wave coming like here, significant part will be propagated, will be forced to retreat, and less part will be propagating downstream. We will see how it works, and the same logic applies here. So, how do we do the maths behind it, and why are these important, of course. So, if you consider a muffler that is basically a simple expansion chamber muffler, it is called simple expansion because there is a sudden area discontinuity and sudden area expansion, sudden area contraction, and it's called simple really because it is nothing but a empty chamber with no lining, nothing, rigid wall chamber, so that breakout noise is minimized from this noise that goes in this direction, that is not allowed. So, basically the structural vibration noise is prevented, and all the structure does is basically when the wave arrives here, lot of part is reflected back and some part is propagating downstream. Again it meets a discontinuity area, again some part is reflected back, some part is transmitted, and there is some kind of a standing wave pattern that is formed here. So, apart from really introducing basically fitting inlet and outlet ports of diameter much smaller than the chamber or the shell diameter, there is nothing much to it. So, that is why it is a simple or as simple as it can get. We will build up on the simplicity or add more complexity to the simple expansion chamber, but before we do that, let us mathematically model the sudden expansion or sudden contraction. Fortunately, for both without any flow, equations that are valid for this one is also valid for this one. So, let us see how we go about doing it. So, sudden expansion. So, if we have a point somewhere here 1 and point 2. So, now we are assuming a one dimensional or planar wave propagation. So, what is the consequence of such an assumption? As we can recall from our very first lectures of this series, when we have a wave whose phase is constant over the cross sectional area, that is, if you are in the small diameter tube, across the cross section the pressure as well as the velocity, particle velocity normal to the plane, they are all constant no matter at which point you are there in the section. So, similarly the same logic applies here. So, the idea is that when the wave expands into such a expansion chamber, basically the planar wave fronts remain planar, that is it is if it is planar here, it is also planar here. Of course, this is just an assumption, and we will see that well, this is valid only below a certain frequency, and even called the cut-on frequency, as you can probably recall from week 2's lecture. But even in the low frequency range, the higher order modes might affect the performance due to what we call as evanescent modes. But we will not worry about that part just now. What we will probably do is, for now, the points, let me use another color for the points listing. This is, say, let me use well, purple color, 1, 2. So, the pressure right at the interface then is given by P1 or P1 tilde is equal to P2. So, the pressure, planar wave pressure is equal to the planar wave pressure here. So, now why is this happening? Because we are actually insisting on the field continuity conditions, that is to say, over this cross section, whatever the pressure is there, the same pressure is there at this point. But then since it is a planar wave front, if we insist that the pressure right here is the same as the pressure just in the point in the chamber, then by the plane wave assumption, the same pressure is carried over on the annular surface as well. So, the idea is they remain plane even when they expand or suddenly they contract. The other important bit or the part is u1, the acoustic particle velocity is constant at 1 and 2. Obviously, you are considering one section that forms one end of the tube, that is a smaller tube, and other end a part of the chamber. So, of course, they are referring to the same points. The acoustic particle velocities have to be constant, that is u1 right here in the direction like this, and this is the direction. They have to be the same because you are referring to the same point. Now, as we were discussing previously, the annular surface area is assumed to be rigid, that is to say, it is a rigid walled annular surface. So, normal velocity is 0. So, you have un is equal to 0 here, with normal velocity over the annular area is 0, because the end plates of the chamber, they are not vibrating, they just remain stationary. So, now u1 is equal to u2, and basically over the port, say the inlet port, but u2, probably I should be writing this as u2 is equal to u1, 2 being the chamber, over the inlet port, that is only over this thing, this small part, and u2 tilde is equal to 0 over the annular area, that is over this thing. So, now what does it mean? If we were to integrate, so we have your u2 is equal to u tilde is equal to u1, we multiply by density on both sides and multiply by the port area, that is SP into SP. So, what do we get? We get u2 u tilde u2 to tilde SP is equal to V1 for the port, and we get this condition, and rho naught u2 SP is equal to 0. Why? Because you multiply both sides by rho naught into S2 well, rho naught into, let us say, the cross section area of the chamber is SC. So, what is the annular area? This area is SC minus ST port. So, when you multiply both the sides by this one, you get this. Now, we will add this and this. So, what do we get? Rho naught u2 tilde, let us say this is, we take this as common, u2 being a function, u2 tilde being a function of let us say r and theta, where r is the radial direction, theta is the azimuthal direction. So, we are eventually left with, when you add this two, SP, this one and this term, they get cancelled, and we are left with only this one, and this is equal to V1 tilde. So, this implies rho naught u2 tilde into SC is nothing but V2 tilde is equal to V1 tilde. So, this is what we get, this is what we get, V2 tilde is equal to V1. So, basically the mass velocity is constant. If you have this kind of a thing, then P2 is equal to P1, that is given, and the field continuity conditions are more fundamental rather than the mass velocity conditions. So basically mass velocity follows from the enforcing the field continuity conditions. So when you enforce such a thing for a rigid end plate, it can be easily shown that V2 is equal to V1 and P2 is equal to P1. So of course in a way you can say this also follows from the continuity equation, because from elementary fluid mechanics knowledge, if you have a port like this and you have sudden expansion, so whatever flow comes here, the same quantity goes here from the conservation of mass. So rho 1 into S1 cross section area times U1 is equal to rho 2 S2 U2. So here it becomes rho naught into S1 into U1 velocity into rho naught into SC chamber velocity, or this is P, and here you have your chamber velocity, say U2. So then you get your V1 is equal to V2. So from the continuity equation you can also see that, but if you want to have a more rigorous mathematical analysis of why this is valid, no matter even if it disregard the higher order modes, if the frequency of excitation is less than a certain frequency, those modes are cut off, that is to say they do not propagate. Only beyond a certain frequency they become cut on or they start propagating. So basically what happens, as long as we are well within the first cut on frequency, that is to say no higher order modes are propagating, only the planar waves are propagating. So higher order modes, as we recall from the last from lectures 3 to 5 of week 2, they have variation across the cross sectional area. So now if we integrate it across the cross section area, the higher order modes in the chamber, and basically add them up, we will see that they in the integral sense. So suppose if you have your u, let us say the normal velocity is given by u and u within the chamber uc. So if you have your chamber like this, so this is uc tilde, so this is r, theta and x is this coordinate or z, whatever you want to say. So the idea is that for higher order modes, if you were to integrate it across the cross sectional area, that is this thing, so only the fundamental mode will survive, the higher order modes will not survive. They will have the entire product over the chamber cross section area will be 0, only the planar wave mode will survive, because the acoustic pressure field or the acoustic velocity fields can be expressed as sum of infinite summation of modes, orthogonal modes. So from orthogonality we can prove that only the fundamental or plane wave mode will survive. So that is the reason why we have your continuity of mass velocity. The same logic actually applies for your sudden contraction also. Here also you have your condition P1 tilde is equal to P2 tilde, and velocity, mass velocity in the chamber is equal to the mass velocity in the outlet port. Okay. So basically we have this kind of thing. Now what is the mathematical implication of such a thing? Finally we can write down the equation P1 tilde is equal to P2 and V1 is equal to V2, regardless of whether they are, this is the chamber, this is the port, or vice versa, this will always hold good. So now if we were to fix the coordinate system somewhere here, well here you have your A1 and fix the coordinate system here at x is equal to 0 here. So e to the power minus j k naught x plus b1 e to the power j k naught x, this one will be 1. So this will be equal to A2 plus B2. So this is A1 and the wave that goes in this direction reflected back is called P1, and this is, and the waves that are transmitted back is called B2, and this is A2. So A1, A2, B1, B2. However, we are considering a certain area discontinuity. So we are technically assuming that this part, actually this part is going to infinity, and this and also this part is going to infinity. It's coming from infinity, it's going to infinity. So it's basically we are interested only at what the interface does without worrying about the lengths of the expansion part, that is this part or this part. We are not worried about that. So we are considering only your interface condition and letting each thing to infinity. Okay. What will happen? A1 plus B1 is equal to A2 plus B2, but then since it is going to infinity, nothing comes back from infinity. So, your this thing will go, will be 0. There will be, because nothing comes back from infinity, there is no reflections back. So, so you get one condition like this. Other condition is mass velocity. So, remember mass velocity was nothing but a1 minus b1 by y1, and is e to the complex exponential evaluate to be unity, because that is where you are fixing the coordinate system to be a2 minus b2 by y2. So, b2 is 0. So, you get another set of equation here. So, what do we do with this? So, to quantify basically the transmission loss as a result of the incident wave and the waves that is transmitted downstream. So, basically what we know is that A1, we know A1, and we need to figure out A2 and B1 from equations 1 and 2. And then let us use these equations to figure out B1 and A2 as a function of A1, that is B1 is some function of A1 and A2 is some function of A1 also. So, how do we get about doing that? We first multiply equation 2 throughout by y1. So, A1 minus B1 becomes y1 by y2 into A2. So, this is what we get, and A1 plus B1 is equal to A2. Okay. We get this. So, now if you simply add this one, this fellow and this fellow, so what are we going to get? 2A1 is equal to A2 times 1 plus y1 plus y2. We are going to get this. So, 2 times A1 into y2 is equal to A2, that is A2 equals 2 times y2 we are going to get this. We have to keep this equation aside, we will call this equation 3. So, what about equation for B1? B1 then is, we just need to subtract A1 from A2. So, B1 will become A2 minus A1. So, you get 2y2 y1 plus y2 times A1 minus A1. So, you get y2 minus y1 divided by y1 plus y2 times A1, and B1 is here. So, or let me write down both expressions for A1 and B1 a little more cleanly. B1 is equal to y2 minus y1 plus y2 into A1, and A2 is nothing but 2y2. Okay. This is what we are going to get. So, what does it mean? So, the reflected wave, or the wave that is reflected back into the constituent element from which it came, that is the reflected wave where I am pointing, this one, B1 is this and A2 is this, and this is A1. So, let us analyze by taking different values of y2 and y1 what happens to this value. Of course, when y2, if you recall, y1 is C0 by S1, y2 is C0 by S2. So, when y1 and y2 are the same, that is the characteristic impedance of the inlet port as well as the chamber are same, what does it physically mean? There is no area discontinuity in such a case. So, basically the port becomes equal to the chamber, the diameters are the same. So, y2 becomes y1, that means B1 is equal to 0. So, if y1 is equal to y2, B1 is equal to 0, and A2 will become equal to A1, A2 will become equal to A1. That means the waves whatever they come, they go through, I mean they pass through completely without suffering any reflections or any phase change, nothing at all, because there is no area discontinuity in such a case. So that is one extreme. Another extreme is basically your when you have a very small port, basically Y1, your Y1 is very small compared to Y2. So under such a situation you can probably ignore Y1 in the numerator. So you will basically get B1 is equal to A1, that is the entire wave is reflected back, and A2, your A2 will become equal to what? You can ignore Y1 and it becomes 2 times A1. So A2 will become 2 times A1 and B1 is equal to A1. So there is a complete reversal of or complete reflection of the waves that come in this thing. But basically these are all extreme cases. What we are interested in is in some finite values, basically what happens for practical systems. Say for example, typically for automotive exhaust systems, the inlet pipe is typically about 40 to 50 mm or maybe 55 for big mufflers, and diameter of the chamber is something like 300 mm or something like that. So that is what we are going to get. So now what does it mean? So if we were to derive a general expression for that, what does it mean? So you get basically, let us derive the acoustic power that is incident on the muffler. So basically if you have something like this kind of a system, the power that is incident at the point 1, that is the acoustic power that is carried by the wave front A1. So what is that? It is incident power expression, if you recall from our last lectures. Incident, so this is 1, this is 2, so this is incident at point 1. So this is A1 mod A1 square by 2 rho naught into Y1, and this is transmission is that one that goes here. So that is nothing but mod of A2 square by 2 rho naught times Y2. If you recall, we just found out what Y2 is in terms of A1. So this becomes then 4 times Y2 square by Y1 plus Y2 square times mod of A1 square. Similarly, we can find out the power that is reflected back, that is nothing but B1 mod square divided by 2 rho naught times Y1. So we need to be correct with our this thing. So actually I guess I kind of forgot this term here, apologies. So then basically this will get cancelled, this will get cancelled, and we will see how all this thing works. And let us quickly derive the expression for this one. So B1 then is nothing but Y2 minus Y1 mod square by A1 mod square divided by 2 rho naught times Y1. Based on our definition of transmission loss, TL is defined as nothing but 10 times log to the base 10 of incident power to transmitted power. So we know now the transmitted power and the power that is acoustic power that is reflected. So TL then becomes 10 times log to the base 10 of A1 mod square by 2 rho naught Y1 whole divided by 4 Y2 rho naught times Y1 plus Y2. So here you are there, the square thing, and this is A1 mod. So this of course gets cancelled, so does A1 square. So if you simplify further, this becomes your Y1 plus Y2 square y1 plus y2 whole square and 4y1 into y2. TL will become this. TL is 10 times log to the base 10, of course, y1 plus y2 whole square divided by 4 y1 y2. So, this can further be written in terms of the areas. So, S1 and S2 they are always positive, so we need not write mod. Now, this is something very interesting. So, why is this interesting? Because transmission loss of a, we know all this lectures I was talking about transmission loss being a function of frequency. Well, it was implied in any case. That is because in some frequencies the transmission loss or the acoustic performance of a muffler is good, and some frequencies it is not. But here you see there is no dependence at all on the frequency. So, why is that? Well, because a kind of semi-infinite elements, and it is a characteristic feature of just a simple area discontinuity in which we assume only planar wave propagation. If there is no reflection, there is only unidirectional wave, and obviously some part is reflected back, but there is no standing wave that is formed in the downstream element. So, as a result, I mean the maths works out in such a manner that the transmission loss of a simple expansion or a sudden area expansion or a sudden area contraction just analyzed in isolation will be independent of the frequency, and it will be basically S1 plus S2 whole square divided by 4 S1 S2. So, actually this will be the same for sudden area, sudden expansion and sudden contraction. Sudden expansion or sudden contraction, they are just the same. So, we can obviously take extreme cases and keep analyzing that, but we can actually deduce some very interesting things. For example, I talked about some numbers. So, like the port area being, say, let us say 50 mm and diameter of the shell becoming 350 mm, really large mufflers for automobiles. So, the diameter ratio is 7 and area ratio chamber to port is 7 square, that is 49. So, what happens here is that if you were to simplify this thing further, you will get 10 times log to the base 10 S1 square plus S2 square plus 2 S1 S2 by 4 S1 S2. Okay. So, what we get essentially is S1 will take 1 by 4 outside, S1 by S2 and S2 by S1 and plus 2. So, 10 times log to the base 10 of 1 by 4. Now, we figured out S1 by S2. So, let us say if this is 49, this becomes 1 by 49. We can probably sort of ignore this part, this bit. So, this becomes 51 by 4, 10 times log to 51 by 4, that is 10 times roughly 13 or so, is just approximate. So, we can basically figure out how much it would be, log of 13. So, we can actually do some calculations and figure out what is log of 13. So, turns out that it is equal to TL is equal to 10 times into 1.1139. So, that is your 11.139 dB, approximately 11.1 dB. So, if you have a sudden expansion like this, it will produce a constant frequency attenuation, which is the constant graph of roughly 11.1 dB for expansion ratio m is equal to 49 or diameter ratio equal to 7. So, we can actually do some, this is transmission loss in dB and this is frequency in hertz and this is in dB. So, we can actually let me go a little further and put some and basically kind of simplify this in terms of the area ratio. So, if we want to call the expansion chamber diameter d and the pore diameter as small d, so this is m. So, obviously d by this thing becomes 1 by m. So, what is the area ratio? This is, so usually if m is large, this is much smaller. So, we can sort of ignore this thing. So, if we were to put this value in here, so TL becomes 10 times 1 by 4 and S1 by S2. So, this becomes m square 1 by m square, and what does this become? This becomes 2. So, we can kind of start ignoring this. 2 is still an approximation, we might just want to consider that. So, then this will become 10 times log to the base 10 of m square plus 2 by 4, where m is equal to d by d whole square. Well, I guess the sudden contraction will also will have the same maths, and I probably leave it for the students to figure out what happens for a sudden contraction. You will get identically the same expression where I have put a tick mark. So, this was the transmission loss analysis for a sudden expansion or sudden contraction, assuming only planar wave propagation. We have not done any lumped system approximation because it is not necessary also. Planar wave will suffice, it is easy to use and all that. And we can also see that using simple maths, we will see that the another one final thing that I want to mention here, that incident energy is equal to transmitted part plus the reflected part. So, the energy carried by A1 square, and this is transmitted part is A2 square, this is B1 square, but obviously you will have some dependence on Y1, Y2, Y1 and those sort of things will be there. So, 1 by 2 rho naught factor gets cancelled, and once you substitute A2 and B1 in terms of A1, you can kind of verify this this identity here. So, with this I will stop the lecture, stop this lecture 4 for week 4, and in the next class we will worry about the simple expansion chamber, that is when this part is combined with this part and you now consider the effects of finite length L. What is going to happen to the transmission loss? Is it going to be increased, decreased, or is it going to, first of all, it is going to vary, whether it is going to vary with frequency or not? All those things we are going to see in a detailed manner in the next lecture, lecture 5 of week 4. Thank you, stay tuned.